So, welcome to the second to last lecture of this semester. So until now, we basically followed the book of Silverman and Tate, and I think we covered basically everything, and I think that's really great. But the last chapter, I don't really like it. It's about complex multiplication, and I think my goal with complex multiplication is to understand the ring of endomorphisms of an elliptic curve. And in the book, well, they don't really talk about what the ring of endomorphisms is, and I don't understand why they treat the topic how they treat it. And so I took a paper. You can find the link to the paper in StudIP. I think I think it comes from a seminar talk that someone gave and wrote an essay about the seminar talk. And it's also based on a lecture by Andrew Sutherland. This is also good source to look at this lecture notes. He also has, so he has this lecture, Elliptic Curves, and I think he gives it every year, and every year he has new lecture notes that you can look at. And they are very detailed, and the exercises are also very nice, so that's also a nice place to look at. So we're going to talk about complex multiplication. So when I first heard of complex multiplication, I think it was in my master thesis, I thought, oh, well, I can multiply complex numbers, what's the problem? But, well, this is where the name comes from. It has something to do with multiplying, and it has something to do with complex numbers, but it's not about multiplying complex numbers with complex numbers. So what is it about? If we have an elliptic curve, for example, this one, and this point with some coordinates, then this here is also a point on the curve. Oh, I said I would wear a mask if someone wears a mask, so I will wear mine now. So what we did until today was multiplying points, so adding points to other points or adding points to themselves, and adding points to themselves is nothing else than multiplying them with a natural number, or even by taking inverse, we can also multiply with negative numbers. So until now, we multiplied points with integers. And this was in a way that when we had x and y rational coordinates, for example, then the new coordinates of n times the point would also be rational. So, but here, the thing is, if x and y are rational, we have an I here. So we have something completely different. We have a map on points of the curve that does something else than multiplying with integers. And as you see, so here it makes sense to call it something like complex multiplication because there is an I, so there's something complex happening. But the question is, we want to know how often does this happen? Well, we won't really answer this question, maybe only vaguely. And when it happens, what happens? So since we know we can multiply points with integers, we know that the ring of endomorphisms on a curve, I will define in detail what that is at least the integers. But the question is, what else can it be? I have another example. The curve x cubed plus 1. And we can call this phi of p. And here, if we have this minus 1 then this is a map on the curve that's not multiplication by an integer. From E to E. Someone trying to get in and can't? Or is this just the lock doing something? So in here again, this is something complex. And also if you maybe realize this I and this are also some pretty nice complex numbers, I would say. Okay, what is the endomorphism ring and why is it a ring? Okay, the second question we will just refer to something. Start with something else. So I give this definition. An isogeny between elliptic curves, E1 and E2, is a surjective, in parentheses, morphism that has a finite kernel. What does this mean? Well, we left out all the part of rational functions and algebraic geometry. So basically, morphism, we never defined what it is. But we can only just see it as maps on the curve that are defined by something rational. And why I put surjective in parentheses, so we can use algebraic geometry to show that this definition is already enough because of this and because of the rational functions, that this is always surjective. And without this finite kernel, a morphism has to be either surjective or constant zero. So with this finite kernel, everything is surjective, but just to keep it in mind, I write it here. So since it holds anyway, we can also put it in the definition. Okay, so basically an isogeny is a nice map between elliptic curves. And what is an endomorphism? A nice map between an elliptic curve and itself. Okay, so multiplication by n is always, for n an integer, is always an endomorphism because it goes from the map from the curve to itself, and its kernel is the n torsion points, and there are only at most n squared of them, so it has a finite kernel. So, of course, this only has to hold for each endomorphism at once and not for all at the same time. And then a small remark that we will not prove. So the endomorphisms of an elliptic curve form a ring. And of course, we have to say, what's the addition and the multiplication? The addition in the ring of endomorphisms is just the pointwise addition with plus as and multiplication is the composition. Okay. Okay. Yeah?
Why don't we allow infinite curves? So what is the intuitive reason to restrict to LRNs and not to general morphisms?
I think we could also just define it as a general morphism, but what would be the problem? Well, we could also define it as a homomorphism of elliptic curves. And I think then everything would basically be the same. So as a group homomorphism, because here we didn't say that it has to work with the group structure. Let me wait. I don't want to say something wrong. Yeah, well, this... Yeah, it's hard to explain this without going too much into theory. So this morphism definition comes basically from rational functions on the curve. And we could also take something else as a condition, but it would always be something that has to do with the algebraic structure of the elliptic curve, so that in the end it works well with a point addition and taking inverses. So something we always need. We cannot do just whatever we want as maps on the elliptic curve. We need something that gives some of the structure. We could also, you could also define an isogeny without the finite kernel and use something else, but then the finite kernel follows from itself. At least if you don't if you don't want maps that are constant zero. But yeah, I think basically this is what we want to exclude with the finite kernel, because with this morphism, and probably if we take the surjective, maybe we need the surjective, then it would follow that everything is either nice as we want it or constant zero. And constant zero, well, we could allow it, but it doesn't make sense here. So that's basically where the finite kernel is needed. And yeah, the nice thing is that there's nothing in between. So there are forget what I said. So one more definition, or just some wording. So I said, of course, the integers are always a part of the endomorphism ring of an elliptic curve. The sentence is not full. The endomorphisms form a ring. Yeah, maybe either we just take this as a black box, or maybe I will put this on the exercise sheet. But this needs, yeah, probably too much background. Let me think about that. So from the definition and the remarks here, we see that the integers are always a subset of the endomorphism ring. And what else we need? We write it like this: endomorphism of E. And the integers are always a subset, because we can just multiply by integers. Yeah? Yeah. Good point. Maybe we have to include that. And we still need that. How did they do that? Yeah, we need that. Yeah, good point. That's the problem if one doesn't take a book as a basis. This is not consistent. Yeah, in this definition, multiplication by 0 is not included. No. They do it like this, but it's wrong. Then let's just say here, or the 0 map. And we don't have a problem here. So then we have the integers as a subset. Thanks. Okay. So as we saw before, it can happen that there's more, and that we don't only have the integers, but we always have the integers. So we can say, okay, we give the elliptic curve some name if it's only the integers, and some other name if it's more. So we say that an elliptic curve has complex multiplication if there is more than just multiplication by integers. So if we have an endomorphism from E to E, that is not multiplication by some n. And then we say the curve has complex multiplication, or CM. So in titles of papers, you will usually not find complex multiplication written out, but usually just CM, which I think is not a good style, but Yeah, there's this video, I think it's on YouTube, from Serre, how to give a good math talk, and he also says you should not abbreviate things, because people might not know what it is and think it's something else. Okay, so why do we say complex multiplication? Well, because this is the usual case, and we will see that there's nothing else. It's always something complex, and we can even say more. So we will now try to find out what's the structure of the endomorphism ring, how does it look like. Okay, so how do the morphisms on the curve look like? Well, on the curve, if you just draw it, yeah, it's not easy to imagine how they look like. But if we go back to the lecture of Julian, then we know an elliptic curve over the complex numbers is basically a torus, or also basically a lattice. So we will see, we will find out how do the maps on a torus look like. Okay, so as we have here in this remark but didn't prove, they preserve the group structure, and it's an endomorphism. And if we use some theory, I think we didn't prove enough here, but we can again use it as a black box. We can prove that an endomorphism, that's an endomorphism on the curve, on the torus, it has to be a holomorphic map. That's nice. Let me say it has to be a nice holomorphic map. What do I mean by that? So if lambda is our lattice, and we consider a map from C modulo lambda to itself, then of course it should be a well-defined function. At least in my definition of well-defined, not in Preda's. So if we, well, it just has to be consistent with the group structure on C modulo lambda, and it has to work out with the modulo part. Everything has to be nice. That's what I meant with nice. And another black box that's more theory now, so let me write black box here. Analytic number theory tells us that maps on the torus like that have to look like this. Okay, so it's multiplication by something, and something is a complex number. And we have another condition, but this is more intuitive. Well, this just comes from the line before. So if we multiply this m to the lattice, it has to stay inside the lattice. There's nothing else than this. Okay. So, well, this looks very nice. M is just some complex number, so it's basically a linear function that multiplies elements on the torus by some complex number, and that it would also explain why we say complex multiplication, because it's multiplying by some complex number. But what's more interesting, we can say a hell of a lot about this M. So, of course, integers can happen for this M. The integers, this would just lead to the integers in the endomorphism ring. So what kind of M can appear? Integers. So if we more chalk, if we just draw the lattice, so these are our kind of base vectors, x and y axis, or imaginary axis. Then, of course, we can multiply by integers. So this, I have no colors. This is our lattice. And if we multiply by integers, we just take some point on the lattice and move it a few steps in that direction. But what can also happen is we have some point here, or well, here maybe, and we rotate it somewhere, for example, to this point, or to this point. This maybe we find something to put it there. Then how would such an M look like? So M times 1 must be in the lattice, because I said M times 1 is a subset of the lattice, and well, the lattice contains 1 and some tau. I think we called it tau. So M times 1 has to be in the lattice, but if M times 1 is in the lattice, also M times 1 must be in the lattice. So there's, oh, these locks make me crazy. So there's a relation between M squared and M and 1 that has to be 0, because being in the lattice means it has to be linear combination of lattice vectors. And if 1 is a lattice vector and M is a lattice vector, and M is not an integer, then M and 1 are also different basis vectors, and we can put this here. So this is a real, totally crazy condition coming from where we allowed all complex numbers, and now we have this because A, B, and C are integers. Why are they integers? Because M squared and M and 1 are linear combinations, are a linear combination. So we have A, B, and C are integers. Here's 0. This means M is an algebraic integer of degree 2. At most 2. Let me say at most 2 before. So what else can we say? I said at most 2. Can it be of degree, well, degree 0 doesn't make sense. Can it be of degree 1? Well, degree 1 would mean that it's either an integer or it's a rational number. But it cannot be a rational number because, well, then it would just not take, for example, 1 to some other integer. Cannot be a rational number. And also not in Z. Okay, next question would be, can it be an algebraic, algebraic number, not integer? We will see that this is also correct, but we will not prove that. So it has degree 2, but the next question would be, is it always complex, or can it also be a real number? Okay, so let's go to the picture and try to think about what happens if m is a real number. Well, this is the imaginary axis, and this is the real axis. So if we multiply by a real number, then we also just move in this direction or this direction, and there only integral multiplication is possible, because then otherwise, again, if we multiply 1 by something that's not an integer, whether it's irrational or not, it will not hit the lattice anymore. So m cannot be a real number. Gesundheit. So actually, m has to be a quadratic imaginary number. So that's also what we see here. I is imaginary quadratic. This is imaginary quadratic. And this is a very hard restriction from being complex to only imaginary quadratic and integral. So those two possibilities can appear. And then one more definition. So if an elliptic curve has complex multiplication, which looks like this, for some m in the complex upper half plane, then we call m a CM point. So why can we always choose m in the complex upper half plane? We can also so if it's not in the upper half plane, then we can just multiply it by -1, and then it will be in the upper half plane. And y cannot be 0 in that case, because if y is 0, then x is a natural number, and then we just don't have complex multiplication. So we can always find an m in the upper half plane if the curve has complex multiplication here for this. And as I said with the abbreviations, I think no one says complex multiplication point. People always say CM point, so this is actually what it's called, and it's not called complex multiplication point, it's called CM point. Okay, so these were a lot of definitions. I will clean the upper board. No, this comes from complex multiplication, but it's still ein feststehender Begriff that is called CM point and not complex multiplication point. So it comes from the word complex multiplication, but it's still called just CM point. So now we will talk about we did the first step in the direction of finding out what the endomorphism ring looks like, and we'll go further in that direction. So we will now look at orders of imaginary quadratic number fields. Let K be an imaginary quadratic number field. This means that K looks like this for some positive integer d, and d is square free. And then a subring of K that's a free Z module of rank 2, this is an order. This is basically just something that looks like the ring of integers. For example, if we have the quadratic imaginary number field Qi that has a ring of integers Zi, and here are no other orders, but this is a free Z module of rank 2 because this is this, and it's a ring, of course, and it's a subset of Qi. And in other number fields, we can have also other forms of Z plus something Z that's a subset of the ring of integers and not already the same as the ring of integers. So just you can just think of the order as the ring of integers or something similar that's inside the ring of integers. And yeah, this also means that it looks like this is the ring of integers. And then we can take C as a positive integer. Yeah, and what I just said is a fact that you can prove using algebraic number theory. So I will write it down as a remark. Every order of K is contained in the maximal order OK, which is the ring of integers. Okay, so now we want to prove this, basically, namely that an order of K always looks like this. And then it's probably a good time to take a break. Okay, every order is of this form. That's what we want to prove. First we prove that all orders are in that form. And then, first we prove that all things in this form are orders. And then we prove that with this construction we get all the orders. Okay. So OK is a free Z module of rank 2. That means that's the lattice generated by 1 and tau. They're independent. And first, we want to prove this is an order. We need this for the second part, but yeah. Okay, first we want to prove that this is an order. So what do we need to prove for this? Well, the fact that it's a ring and the Z module and rank 2 and everything follows from the fact that OK has rank 2 and the free Z module. The only question is, what happens if we multiply numbers? Do they stay inside after multiplication? So we take 2 elements of here, multiply them, and see what happens. Take A plus CA prime, B plus CB prime in there. So A and B are integers, and A prime and B prime are in the ring of integers of K. And then we just multiply them. Okay, and what do we get here? We get A, B plus C times A prime B plus A B prime plus C A prime B prime. And of course, since C is an integer, C is an integer, A prime and B prime are in OK. Since also integers are in OK, then this whole thing is in OK. Here's our C, and A and B are integers, so A and B is also an integer. So this is in here. So part 1 is OK. And part 2 would be, are all orders of the form C plus OK. Okay, so what is an order in there? It's a free Z module of rank 2. It's a lattice, so it must be a sublattice of OK. And if OK is generated by 1 and tau, let me say order is a sublattice of OK. And an order is also a subring, so it has to contain the 1. So it's a subring by definition. Oh, I didn't give a name to the order. I just write order. So then we go into this order and look for the smallest positive integer, such that look in the order. For smallest positive C prime, such that C prime tau is in our order. So since this is possible, since if we draw a lattice, no colors. If this is our lattice, then a sublattice is could be, for example, every second row and every second column. So a sublattice is a part of the lattice where we leave something out. So this means if this is our tau, and if we have a sublattice of this lattice, then there is an integer C prime, such that C prime times tau is in our sublattice. So we find this C prime. But this means, and C prime is an integer, so C prime is, because it's on this line, also in our base lattice, because it's a subring and contains the 1. So 1 and C prime tau are in our order. But this means our order contains this, because tau is in our OK, C prime is this, and this is exactly what we wanted to show. Okay, so this was totally independent of elliptic curves. It was just that an order of a quadratic imaginary number field is always of this form. And now what we actually want to look at, but this is also without a proof. An elliptic curve over C has one of the following endomorphism rings. So either the integers, as we saw before, or the ring of integers of a quadratic imaginary number field, or something a bit smaller. So an order in an imaginary quadratic number field. So I left out a lot of proofs here, which is probably the reason why it's not in the Silverman Tate book, because it's not really easy to prove this just in a small chapter. But I think this is one of the important things to remember. The endomorphism ring of an elliptic curve is either the integers or the order in an imaginary quadratic number field, which is basically something that looks like the ring of integers or similar. Okay, let's take a break until 11:15 maybe. And I will get some chalk.
Das folgt alles direkt aus. Also wenn man annimmt, dass es Morphismus von Kurven ist, dann folgt aus, wenn er nicht konstant ist, alles. Also dass es Surjektiv und endlichen Kern hat. Also, aber wenn man es definieren möchte, sollte man es halt schon mit dazu nehmen.
Aber dann folgt auch schon, dass es nicht die Nullabbildung sein kann.
Nein, die Aussage ist, ein Morphismus zwischen Kurven ist entweder konstant oder Surjektiv und endlichen Kern.
Genau. Aber der definiert dann einfach nicht die Endomorphismen als Isogenien, ne?
Nee, man definiert Morphismus einfach als Morphismus von projektiven Kurven.
Ohne dass es eine Isogenie ist.
Und dann, so nennt er.
Ja, aber dann kann es ja trotzdem die Nullabbildung sein.
Also,
Warte mal.
Also das ist auf jeden Fall nicht der springende Punkt. Der springende Punkt war aber auf jeden Fall, ist es entweder die Nullabbildung oder erfüllt all diese Bedingungen.
Genau.
Und das war das, was ich mich gewundert hatte, warum man die alle annimmt. Aber es ist nicht wirklich notwendig, die anzunehmen.
Weil sie schon folgen.
Aber halt, das erfordert schon ein bisschen. Das haben wir nicht mehr. Den Satz hatten wir so kürzlich mal die Partial Geometrie, aber den haben wir nicht bewiesen.
Das ist auch mega krass. Also man könnte ja auch meinen, man könnte einfach sagen, ich gucke mir alle Gruppenhomomorphismen an. Aber da gibt es, glaube ich, auch Probleme, die auftauchen, die man dann nicht haben will. Oder man muss dann, ich weiß es nicht. Auf jeden Fall ist es im Prinzip schwierig, den Endomorphismenring zu definieren, ohne irgendwie ein bisschen Theorie. Deswegen war ich auch ein bisschen aufgeschmissen mit deiner Frage.
Ja, und das war nur, weil ich mich das schon gewundert hatte. Letzte Woche war Julians Vorschlag, warum man Isogenien so definiert, weil das ja doch irgendwie sehr spezifisch scheint.
Ja, ich meine, wenn man es eigentlich als Morphismus im Sinne von, das ist eine rationale Abbildung auf Kurven definiert, dann macht man da ja im Prinzip schon mega viel Vorarbeit. Ja, genau. Weil das auch schon sehr viel einschränkt.
Ja, es schränkt so weit ein, dass es eigentlich die sind.
Genau.
Also, sobald sie halt den Punkt noch fixieren, dann können sie noch die eigentlich.
Genau, dann muss man noch muss man den unendlichen Punkt noch machen. Aber den haben wir ja von ab. Ich muss mal Kreide holen gehen. Ich hab doch Pause gedrückt.